Hey, Jenny Nong, it's Team Training Wheels. This is our final spring presentation. Of course, I'm Tyler Chandler.
I'm Brian Lee.
I'm Chase Barbe.
I'm Cullen Lee.
I'm Fernando Hernandez.
Caleb Lindsay.
Bradley Goforth.
Greg Deichley.
Tristan Nairn.
So here's our agenda we have laid out for this final presentation. We're going to start with just a brief team introduction. I'm not really going to talk about everyone's positions and what they've done. I'm just going to kind of show you guys so you guys can look back over and see what everyone has accomplished. We're going to then move into fall 2019 accomplishments, just a brief overview of what we did last semester. We're going to then move into the current semester objectives, final schedule, final budget, and bill of materials, frame and FEA update, hand calculations, in-house manufacturing, partial assembly, adapting to new circumstances, introduction to work instruction guide, and then within the work instruction guide, we're going to have a couple slides on steering, drivetrain, shell, innovation, and then we're going to round things off with some final thoughts and acknowledgments. So like I said, this is the team and their responsibilities for the senior design requirements.
So for the fall 2019 accomplishments, the sole purpose of the design was to design every component, test the component, and perform analysis on every component that goes into the HPV. So the team designed the frame, the steering, brakes, electrical, the fairing, drivetrain, wheel placement, and ergonomics, as well as tested finite elemental analysis, did CFD on the shell, proved that every component works effectively and efficiently, and everything was ready so that come spring semester, everything was ready to be purchased and assembled.
At the beginning of the semester, we had several objectives we wanted to achieve. Before COVID, we wanted to safely assemble the human-powered vehicle and perform rider optimization analytics on the completed vehicle, and also competitively represent Lamar University's Department of Mechanical Engineering at the HPV competition east in Georgia. Unfortunately, due to COVID, we had to adapt and learn how to collaborate remotely. We had to satisfy new requirements set forth by senior design sponsors. And we wanted to create a work instruction guide to assist future HPV teams, even though we couldn't compete. And we wanted to give a thorough presentation communicating how well-rounded mechanical engineers complete a senior design project. And lastly, achieve an A in the second course of senior design.
So, of course, with any project, you're going to have a schedule. And with the schedule, we want it to be as fluid as possible. Things come up. Especially in senior design, we were also balancing a regular class load. So a lot of these schedules changed pretty frequently throughout both semesters. And what this schedule reflects was normal manufacturing preparation for the ASME EFES competition. And it also represents the change the new requirements set forth by the senior design advisors. So as we can see, the top schedule was a kind of a snapshot from February to March. Really, when we were doing most of the manufacturing, you can kind of see, February we were kind of busy, and then towards end of February to March we kind of had a lot of midterms, so we weren't really doing much manufacturing. But then we picked it up when we came back from spring break. But unfortunately, that's when COVID-19 happened. So the schedule below, we can kind of see. Pretty much we've been working this, since we got back from spring break till, today on satisfying, the new requirements.
So for the budget, everything changed after our competition got canceled. That saved us about $3,000 from that. And we also, at the beginning of the semester, we didn't really know how much material would cost. So we just gave a blind estimate. That's where we came up with our $7,500. And after we actually got quotes from vendors, we came up with a bill of material, and then so our final budget came out to around $2,000. So with our BOM, put the BOM together as if another team were to pick up our project, they could just order these parts from the vendors and start where we left off.
So with the frame, as with most other things in this project, a lot of changes were made throughout the process. Our final design last semester integrated a suspension system as well as some complex tubing bends into the frame. As this semester progressed, we found that we had both kind of a lack of resources and access to special tooling. So we redesigned the frame to make it a little more manufacturable, especially for us as students, and also to help reduce the budget and stay with our current funding. So this is our final frame design and what was actually fabricated. We also obviously repeated all of our analysis of the frame using Fusion 360. We used multiple different load scenarios with different drivers of, different weights, different loadings, and obviously also we performed analysis required by the competition. Through this, we found that our minimum safety factor of the frame was a 2.8. We believe that this frame not only obviously meets the requirements of the competition, but also provides a stable and reliable platform for everyday use as a consumer might want it.
Here's a few of our detailed drawings from Fusion 360. This slide contains mostly detailed drawings of our RPS, which is our roll protection system. These detailed drawings contain the bike spindles, the drivetrain placement, the front legs, the steering tire rods and heim joint, and then also the mainframe tube. And then these are the rear arm, the rear wheel mount, and the seat bracket detailed drawings.
So for our hand calculations, we wanted to correspond them to our FEA analysis. We had to make some assumptions. Our first assumption was that we're going to be running at 100 RPMs. We set a target speed for a top speed of 35 miles per hour, and our target cruising speed was going to be around 15 to 20 miles per hour. Our wheel diameter was 20 inches with a circumference of 62.8 inches. First, we had to calculate our gear development, and once we get our gear development, we can actually calculate our gear ratio using that assumption speed of 35 miles per hour. Our gear ratio ended up coming out to 5.87. After that, we found our T allow to give us a value of 45,000 PSI. Using that T allow, we were actually able to find our design diameter for the bike, which we ended up getting 0.09 inches. For the actual diameter that we're going to use for the pipe, we were going to use 0.25 inches. So this calculation falls in line with what we want to use with a fair safety factor. After that, we wanted to find our stresses on the frame of the bike. So we decided to find the bending force on the bike based off of the driver's weight. We also corresponded a little bit of impact from actually driving the bike itself. After finding sigma bend on the bike, we ended up coming out with 48.7 KSI. After that, we wanted to find our allowable force our frame was actually able to withstand, with an allowable force coming out to 61.5 KSI. So the bike was actually able to withstand more than enough bending stress and more than enough force from the rider itself.
So some additional hand calculations that we worked on. We wanted to really figure out if our weld between our main frame tubing and our drivetrain was going to fail. So as you can see through the process, we made a few assumptions. We checked for yielding at the frame bend before we could consider the rider's weight affecting that weld that was between the main frame tubing and the drivetrain. So after we checked for yielding, we then calculated the max force carried out by the weld, which was a Mech 2 concept, and then from there we were able to determine the stress at the weld, and then we were able to compare the two and figure out that our weld would not fail given the amount of force applied to the pedals. Another thing that we also calculated was our braking calculations, our braking factor, our braking force, the acceleration needed to slow down and satisfy the ASME requirements of achieving a speed of 25 kilometers an hour within a distance of 5 meters. So through these braking calculations, it was proven that, with this established force that we were able to stop within 5 meters.
So from the beginning, our team had a pretty good idea of what we wanted to do. We were given a bike from last year that we could have used and that we planned to use several pieces of. However, as a team, we wanted everything to be our own unique design, kind of be able to determine how how everything was laid out ourselves. And, we kind of wanted to bring something new to the table that was unique to our group alone. So before this whole virus thing came up, we were well into the building process. We started with building a layout of what we had kind of as our vision in our head. We built that in Fusion. We just took some rough measurements from the old bike that we were given and used those to kind of give us an idea of what our realistic measurements would be. So we took measurements in the beginning. That was mainly last fall. However, this spring, we began taking those measurements and actually putting them, bringing them to life, I guess you could say. We bought all the material, got everything purchased, and then we used the science building there at Lamar, and we used a lot of the machines like the bender, the pipe bender. The MIG machine was used a lot. And we got everything bent to what we wanted, or actually pretty close to it. Go ahead and go on to the next slide. We actually had, so as all things go, when you build something from scratch, nothing ever turns out exactly how you originally draw it up. So once we got everything bent and everything tacked with the MIG machine, we did the research and found out that in order to have the strongest weld possible on chromoly, you would have to use TIG welding. However, nobody in our group was very educated with TIG welding. We kind of used our resources, branched out. There was a member from the Baja team this year that said he knew how to TIG weld. So myself and several others went over spring break right before the virus popped up, and we met up with him, and he actually welded our frame and helped show us a little bit about TIG welding as well. So not only was it productive for our project, but we actually got to learn a little bit as far as TIG welding goes. Throughout this process, a lot of grinding was done. Obviously, when you're welding, a lot of grinding is going to get done. The MIG machine was used to do the tacks and the main welds for the roll bar or the roll cage. And just because that was mild steel, and a MIG machine is going to do just fine with that. So there was a lot of grinding there. Everything that we cut was mainly through a bandsaw. There was a little bit of stuff that we cut through with a grinder, but that was very, very minimum.
So throughout building the frame, there were several things that we had to kind of overcome and figure out a way around, obviously some of the problems came with, for one, like I said before, the frame having to be TIG welded in order to be at its strongest point. But another thing, it's something small, even like notching the pipe for welding. Obviously, if you butt up a pipe to the other end and you weld that gap closed, there's not going to be any air within there, which in order to have an arc, you have to have air. So that was one thing that just not a lot of people would think about. And we felt that it would be a good piece of information to add into the slide. And it was something that was very helpful. Go on to the next one. So as I said before this whole coronavirus thing, we were well on our way into the building process. The frame was completely done and welded. The front end of the bike was completely assembled. And in all honesty, the back end wouldn't have taken but probably, well, not just the back end, the bike to completion would probably have only taken a couple more days work. However, as you can see in the picture to the left, that was how much of the bike that we had assembled already. And as I said, the back end would not have taken very long at all. And then the bike to completion.
So for the show, we decided to use PEX and polyurethane to wrap around the PEX. These are both very light materials, so they're easy to work with, and polyurethane is also very strong. So we decided to use this instead of fiberglass just because it's a lot less weight and it's easier to work with. And it's very cheap as well. It only costs about $116 for all the materials. We actually ordered everything for this and we received everything. And we were about to start the assembly for this, and then that's whenever we had to shut everything down because of the coronavirus.
As Colin mentioned before, we had to adapt to new circumstances due to COVID-19. So that caused us to reevaluate pretty much the entire assembly for the HPV, which caused us to do Zoom meetings, much like we're doing right now. The group's overall health and safety is the most important part, so which is why we just focused on the new requirements as opposed to trying to actually go into the lab and all meet at once or potentially risk our health. So we just decided to do the new requirements, which caused us to communicate even more so that we're all on the same page, because even more than ever, we're all communicating from far distances. As future engineers, it's important to adapt and overcome for unforeseeable obstacles, much like this COVID-19 that pretty much no one expected to happen this year.
Now, due to the impact of this COVID-19 pandemic, as previously stated, we weren't able to finish our project. So we decided to help the future team that will inherit our design in finishing the project to our standards. So we decided to create a work instruction guide. Now, basically all this is a instruction manual to help finish each section that we didn't have time to finish, such as electrical, chain, steering, and shell. And then, of course, the innovation. All of it is subject to change due to whatever the future team wants to do with the design. But we decided to take it into our own hands and help them in the right direction. So basically all this instruction guide is going to do is it's going to have a brief overview of the project itself. And it will have detailed instructions on each piece of the project, each section. And that way they can have no confusion. They're not jumping in blind. And they can get things rolling a little bit easier than we were able to.
So for the steering was meant to be completely manufactured in-house. It's designed for the driver to be comfortable. It was intended to have a 70-degree turn radius to where it won't hit the shell and able to make sharp turns. The semi-conventional type of steering for HPV competitions, and it provides a uniform turning capability that reacts immediately to the driver so that both wheels react at the same time.
So as Greg spoke of earlier, we performed some hand calculations and did some research before we planned out our drivetrain. Based on our calculations, we determined some ideal gear ratios to reach our desired top speed and cruising speed based on possible cadences and comfortable cadences for a human. So we determined that we'd like a 52 tooth and a 32 tooth chain ring for the front, and a ratio to meet our ratios we need between 11 and 23 tooth chains on the rear. So with that in mind, when we selected our drivetrain, we kept all those parameters in mind and selected what we thought would be the best choice to meet all these specifications. And we have our table of gear ratios over here on the side. Now, once we had that selected, we had to make sure we were properly installing it and everything was going to work together. So we developed the drivetrain placement diagram to ensure that everything would be placed ergonomically and safely. We could keep the chain out of the driver's legs and would just ensure that it would be properly fit and be safe for any driver of any size. And all this is included in the assembly instruction guide developed by the team that Tristan just spoke of.
So as I was saying earlier, for the show, we were going to use PEX and polyurethane. The PEX is very flexible, so you really don't need many fittings. So you can pretty much just bend it around. And you might need a couple fittings for T's and a couple elbows, but we're planning on just bending it around the frame and attach it using very thin metal wire and wrapping that around the frame. And then for the polyurethane shell, we're going to cut that into sections and just do a little section at a time and use a heat gun to heat up the polyurethane so it can form to the metal or form around the frame of the PEX frame. And we're going to also put a plexiglass windshield in so we could see, and it was going to hinge so you could get in and out from where the windshield is. And we're going to put a trunk in the back that would also hinge, and that was going to store the battery. And
When you think of innovation, you think of what sets you apart from somebody else. So Team Training Wheels wanted to take this to the next level of having a certain cool factor as well as being completely different than anybody else. So our innovation was going to be an intricate electrical system. We were going to have 2 lithium batteries similar to what is ran in power tools such as like an electric drill, electric impact, things such as that. We were going to run 2 12-volt batteries in parallel to give us double the cranking amps and things such as that. Now, the things we were going to run would be, we're going to have left and right blinkers. We're going to have a horn, a cooling fan just to blow on the driver, a 5-point racing harness. I already spoke over the batteries. We were going to have 2 solar panels. So these solar panels were going to be hooked up to where they would trickle charge the batteries themselves. And then, as Caleb just mentioned, a trunk storage compartment and a trunk dome light. The dome light would be able to illuminate in the trunk, giving you, room to see and everything such as that. And the schematics of the electrical system can be seen right there on the slide. Each item will be grounded to the frame itself. The power wires will be ran to a switch panel, a control panel, and those would control each of the objects. The only one that would not be on that control panel would be the blinkers, and those would be on a motorcycle style 2-way switch on the steering handles.
Just to kind of round things off here, the ending to our project due to COVID-19 was not really anything that we could have, budgeted for. We couldn't have planned for it, even designed with in mind. Basically to put forth countless hours of dedication and effort and have it immediately cut off is, it's disappointing to say the least. But, our team wanted to end the senior design project with the, betterment of future MECI seniors in mind. So what we kind of did to the poster was we attached a QR code that leads to the work instruction guide. In that work instruction guide, it details necessary steps that, another HPV team could come in and they could pick up where we left off, and they could finish our HPV like our team intended to. Even though we didn't have the opportunity to compete at the ASME eFest competition, our team would like to take a moment to thank all of our donors as well as our project sponsors, professors, Jenny Zhao, Kendrick Ong, and most importantly, our lab instructors, David Day and Walker Wheeler. So again, we thank you for a very interesting and adaptive past 2 semesters. Have a nice day.